This video is over lesson 26 for my pre-algebra classes. Its title is Transformations. A transformation is any operation on a geometric figure. I'm going to pause there for just a second because normally when we use the word operation in mathematics, we're talking about addition, subtraction, multiplication, division. Well, that's good for arithmetic, where we're taking a number plus a number minus a number, and so on. But when we have geometric figures, you can't take a line segment and add it with another line segment. You can add their lengths, but not the segments themselves. You can't add a triangle with a triangle. That just doesn't make sense. So in this case, a transformation is an operation on a geometric figure, and so this means to alter its position, and I can do a better S than that. Let's fix that up. Its position, there we go, that's better. Its orientation, so its position where it is, its orientation where it's pointed, its size, or its form. So basically a transformation is we're doing something to alter that figure in some way. It is no longer the same figure in the same location, something is different. Now, congruence transformations are where we usually focus our time when dealing with transformations, because congruence transformations are special because they result in congruent figures. And as we learned about in a previous lesson, congruent figures means that they have the same shape and size. Congruence transformations are also called isometries. And that's plural. If this was singular, the IES would turn back into a Y, just like we see here. So in the word isometry, iso means same, and metry means measure. So isometry literally means that they have the same measure, which is why when you've done an isometry, you have congruent figures. There are three isometries. The first isometry is commonly known as a slide. Its actual name, its more technical name, is a translation. And so if you think about translating from one language to another, it's as if you're sliding from one list of vocabulary, one set of rules for grammar, and sliding into another. So a translation is a slide. So down here I have the triangle ABC. And symbolically we would write that by actually drawing a triangle and the letters ABC. And it is read, as we just said, triangle ABC. And this is our original figure. We haven't done anything to it yet. This is before the transformation, before the translation in this case. So the prefix pre means before, and then we have image. So pre-image. The original figure is the pre-image. So triangle ABC here is my pre-image. And we're going to translate this. I'm going to try to get this out of my shadow a little bit here. So we are going to translate this right 3 and up 2. And this is real simple. We're going to take the point A and literally do what it just said here. So I'm going to go 1, 2, 3 to the right, and 1, 2 up. And there is my new transformed point, my translated point. Now, since this came from A, we want to identify that, and the way we do that in geometry is we give it the letter A again, but we can't just leave it there because otherwise we'd be saying these are the same point, but they're obviously not. They're in two different locations. So what we do to say that this is the new A is we put a tick mark on it. I know it looks like a 1, but it's really more of a tick mark. And we call that prime. So this is A prime right here. So now if I take B and do what this says, so right 3, 1, 2, 3, and up 2, 1, 2, this is my new B. So this will be B prime. And then finally, 1, 2, 3 to the right, up 2. This would be C prime. And if I connect the dots, my new triangle would be written like that symbolically. So we'd have all those tick marks. And it would be read as triangle A prime, B prime, C prime. And if triangle ABC is the pre-image, then triangle A prime, B prime, C prime is the image. And what you should notice here is, given a little bit of human error, these two triangles are pretty much identical. Now we can represent translations with coordinate notation. And so to help us out here, we're going to go through and find the coordinates for A, B, and C. So starting from the origin, I would have to go left 1 and up 1 to get to A. So left 1 would be a -1, up 1 would be a +1. B is left 2 and down 1. So left 2 would be a -2 for the x value, down 1 would be a -1 for my y value. For C, I don't go left or right at all, so that's 0 for the x value, but I do go down 2, so that's a -2 for my y value. Now let's find the coordinates for all of our primes. So A prime, B prime, and C prime. For A prime, I have to go 2 to the right, so that's a +2 there, and then 1, 2, 3 up, so 3, +3 for my y value. B prime is 1 right and 1 up, so that's a +1 for both of those. And then finally C, I go to the right 3, but I'm not going up or down at all, so that'll be 0 for my y value. Now, ladies and gentlemen, if you look here for just a second at the x values. So -1 moved over to 2. -2 moved over to +1. 0 moved over to 3. If you examine these, you'll discover what must be happening here. And hopefully what you've realized is it looks as if we've taken each of these x values and added 3 to get these new x values. In fact, that's exactly what we've done. I've taken my -1 x value and added 3. I've taken my -2 x value and added 3. I've taken my 0 x value and added 3. So -1 plus 3 is 2, -2 plus 3 is 1, and 0 plus 3 is 3. Now if we do likewise, focus in on our y values, so I'm going to cover up the others. Focus on the y values. Maybe you can already guess what's going to happen here, but 1 needs to become a 3, -1 has to become a +1, and a -2 has to become a 0. Well, what's happening here? Well, we're adding 2. So right and left will affect our x value, up and down will affect our y value. So it looks like I've taken the y value 1 and added 2 to get 3, the y value -1 plus 2 to get a +1, and the y value -2 plus 2 to get 0. So using this, hopefully we've discovered now what the formula is. Now, quick word, notice that we do use arrows sometimes in geometry. This is a geometry symbol. It is not an algebra symbol. So this would not be okay in algebra, but geometry is a slightly different creature. So what's happening here? Well, whatever my x value is becoming that same x value, but this time plus 3. So this would be x plus 3. My y value is getting added to it. So whatever point you start with, to find its translated point, its image, we would add 3 to the x value, add 2 to the y value, and there's your new point, your prime point, we could call it. So ladies and gentlemen, I'm going to ask you at this time to go ahead and pause the video and give this a shot. See if you can figure out what the formulas for these 4 would be, and then go ahead and hit play and see how you did. All right, here we go. For the first one, left 1 is going to affect the x value, but left is a negative direction, so it'll be x minus 1. Up and down affect the y value. Down, though, is a negative direction. So x comma y goes to x minus 1 comma y minus 6. Down here, right 5, down 4. So left and right affect the x value. Right is a positive direction, though, so x plus 5. Up and down affect the y value, but down is a negative, so y minus 4. So x comma y goes to x plus 5 comma y minus 4. Over here, up and down only affect the y value. So nothing's happening to the x value, so it's going to stay the same. But my y value, up is positive, so plus 7. Down here, left affects the x value, left and right affects the x value, so it'll be x, left is negative, so x minus 7. Nothing's happening to the y value, so just y. If we flip the page, we'll move on to our next isometry here. So this isometry is commonly known as a mirror image or a flip. So if we have a mirror image or a flip of something, that is its reflection. Reflection. And so the idea here of a mirror is very important. So if we imagine that you're looking in the mirror, one of the important concepts of looking in a mirror, so if my pencil here were my mirror, if I have my finger over here on one side of the mirror, it looks like the mirror image is the same distance but on the other side of the mirror. So its image will be on the same side, or excuse me, the same distance from the mirror, from the line of reflection it's called, but on the other side. So our first example here, we're looking at reflecting over the y-axis. We're going to reflect over the y-axis. So that means that the y-axis is my mirror. So if we start with point D, move towards the mirror, move towards the line of reflection. So I can go 1, 2 spaces towards it. So its reflection should be 1, 2 spaces on the other side. There's my D prime. E is 1, 2, 3 spaces away. So its reflection will be 1, 2, 3 spaces on the other side. There's my E prime. And finally, same thing with F. F is 1, 2 spaces away, so 1, 2 on the other side. There is my F prime. And when I'm all done and I've connected my dots, we should have a new triangle where it looks like if we were to fold this over along the y-axis, it should look like these two would match each other perfectly. And with a little bit of human error, it does. If we take away that little bit of human error, oops, I forgot my prime in the F. Don't forget your prime. Well, ladies and gentlemen, there is a formula for this as well. So let's take a look at this guy here. So D, I have to go left 2, so that's a negative 2, and then up 2, so positive 2. E is left 1, 2, 3, but then up 1. And then F is left 2, but does not go up or down. Now just take a moment real quick here. You'll see that we need the coordinates for D, E, and F again right here. So might as well copy those over right now while those are fresh in our minds and we're thinking about it. And then down here we will also need to copy those values down. All right, so back up to here. Let's find our primes now. So d prime is 2 to the right and 2 up. E is 3 to the right, so positive 3, and 1 up. And then F is 2 to the right, but no up or down. So if we take a look here, ladies and gentlemen, one of the things that should stand out first is my y values of 2, 1, 0 stay 2, 1, 0. So it looks as if the y value, when we reflect over the y-axis, the y value stays the same. But if we think about how to describe what is happening to the x value, when I got a negative 2, it becomes a positive 2. When I got a negative 3, it becomes a positive 3. When I've got a negative 2, it becomes a positive 2. It seems like these are just becoming their opposites. And that's exactly what's happening. And so algebraically, we express that with a negative, because negatives really mean opposite. So a negative x really means the opposite of x. So the opposite of negative 2, positive 2. The opposite of negative 3, positive 3. Opposite of negative 2, positive 2. All right, now we're going to reflect over the x-axis. So d, we're moving straight towards the x-axis, is 1, 2 away. So 1, 2. On the other side is my d prime. E is just 1 space away. So 1 space away on the other side, that's my E prime. Now F is special. F is special because it's touching the line of reflection. So if you think about a mirror, if I've got one hand or one finger that's touching the mirror, doesn't it look like the other side is touching back? And so if we touch our line of reflection, the reflection is right there with us. So anytime you've got a point that touches your line of reflection, it will be its own reflection. So F and F prime are the same point. So connect the dots. And it should look like if we were to fold along the x-axis, we would get the same triangle. And it does. So getting the coordinates here, d prime is 2 to the left and 2 down. So 2 left and 2 down. E is 3 to the left, but this time 1 down, so that'd be a negative 1. And then, well, F, remember F prime didn't move. So it's still negative 2 comma 0. So this time if we look at it, hopefully what stands out to us is the x values didn't change. So negative 2 is still negative 2, negative 3 is still negative 3, negative 2 is still negative 2. So what happened to my y values? Well, if you think about the last one, you probably have a pretty good hint. They become their opposites. So when you reflect over the y-axis, the y values stay the same, but the x values become their opposite. When you reflect over the x-axis, then the x values stay the same. It's the other ones that become their opposites. All right, ladies and gentlemen, we're going to take a look at a few more reflections, but this time getting away from the x-axis and the y-axis, so these are a little more unusual, which is why we're not going to worry so much about the formulas. The next one is DF. We're going to reflect over DF. So segment DF is part of this line, this vertical line that goes through that side. So that's my mirror right there. Well, ladies and gentlemen, if you remember our rule, then anything that touches the line of reflection will just reflect onto itself. If you can remember that, then you already know that D and D prime must be the same, and F prime must be the same. So it's really just a matter of finding the reflection of E. Well, E is only 1 space away from our line of reflection. So 1 space on the other side will give us our E prime. Down here, we're asked to reflect over the line x equals negative 1. So if we think about all the places where x is negative 1, well, obviously x is negative 1 right here. Negative 1 comes 0. It's negative 1 here, at negative 1, comma 1, negative 1, comma 2, negative 1, comma 3, negative 1, comma 4, negative 1, comma negative 1, negative 1, comma negative 2, negative 1, comma negative 3, negative 1, comma negative 4. And this goes on forever. And so if we think about connecting these dots, you're going to get a vertical line. So whenever you have an x equals something, it's going to be a vertical line. So if that's my mirror, then to find the reflection, remember we're going to go towards it and then go the same distance on the other side. So D just moves one space towards it. So one space on the other side is my D prime. E is 1, 2 spaces away, so 1, 2 spaces on the other side. And then finally F is 1 space away, so 1 space on the other side. I'm going to make this a little darker here since that's on the axis. And we should see that if we were to fold this over on that dotted, dashed red line, these two triangles would match up perfectly. Well, ladies and gentlemen, if x equals a number gave me a vertical line, it should make sense then that y equals a number, like in this next example, should give me a horizontal line. And sure enough, it does. Because if you think about the values of all the points going horizontally here, they all would have a value of y equals negative 1. So now let's move towards our mirror. So D is 1, 2, 3 spaces away. And so I'm going to go on the other side, 1, 2, 3 spaces. There's D prime. E is 1, 2 spaces away, so 1, 2. And then F is 1 space away. So 1 space. And then finally, this one's special. We're going to reflect over the line y equals x. Y equals x is special, partially because we're saying that all the y values have to equal the x values. Well, that's going to be true at 0, 0. That's going to be true at 1, 1, at 2, 2, 3, 3, 4, 4, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3, negative 4, and on and on and on. And so we don't have a vertical or horizontal line like we've been doing. This one is at a diagonal, which means as we approach our line of reflection, we have to approach at a diagonal as well. So how many diagonals is D away from my line of reflection? Well, there's one diagonal, there's 2. So 1, 2 diagonals on the other side should be my D prime. E is 1, 2, so 1, 2 on the other side is E prime. And finally F is just a single diagonal, so single diagonal on the other side. Connect my dots. Now if we look at the coordinates for this, D is at 2 to the right and 2 down. So 2 right, 2 down. E is at 1 right, but 3 down. So 1 right, 3 down. And then finally, F prime is not going left or right, it just goes down 2. If you compare your x values and your y values, hopefully you see what's happened here. It looks as if the x and y values have just switched. So x comma y will move to y comma x. So if we reflect over this line, it just switches the x and the y values. All right, for our next isometry, we're looking at a turn or a spin. So this is a rotation. a rotation. So one thing that it's important in mathematics to take into consideration is that a positive rotation is actually counterclockwise. And a negative rotation in mathematics is clockwise. So when it comes to these, it can be helpful to ahead of time kind of think through where are your points. So J is at 2, 1, K is at 3, 1, and L is at 1, 1. So ladies and gentlemen, if I rotate this 90 degrees around the origin, then my figure here is going to move from this quadrant, this first quadrant, 90 degrees counterclockwise because it's positive, will take me over here to this second quadrant. So here's what I'd like you to do. I'd like you to take your paper, and since we're moving to the second quadrant, I want to rotate my paper so that the second quadrant now looks like it's in the position of being the first quadrant. So we're going to make that second quadrant look like it's the first quadrant. Okay, it's not, but we're going to make it look that way. So now we're going to take these points, these coordinates that we had just thought through a moment ago, and we're going to graph them in their new position. So J was 2, 1, so I'm going to graph my new 2. Oh, I got that backwards. I'm sorry. Why didn't anybody correct me? Oh, right, it's a video. Sorry. J is 1, 2. I don't know how I did that earlier too. All right, now that we got that fixed. So J, I'm going to plot in my new 1, 2. I'm going to plot K in my new 3, 1. And then I'm going to plot L in my new 1, 1. And then we can connect the dots. Now if I return this to normal, and I put my labels in here, so obviously the right angle is my L prime. The K was that real sharp point, so this must be my K prime. And so odd man out, this must be my J prime. Does it look like we've taken this and rotated around? Yes, it does. So over here, and we can reuse these same points here because it's the same triangle, a negative 90 degrees around the origin is going to take us clockwise, so from the first quadrant down to the fourth quadrant. So I'm going to turn my paper so that the fourth quadrant looks like it has become the first quadrant. And then we're going to plot those points again. So in my new position, I'm going to plot my new 1, 2. I'm going to plot my new 3, 1, and then my new 1, 1. So connect the dots. And if I unspin this, obviously the right angle will be my L prime, the real sharp angle will be my K prime, and odd man out must be my J prime. Does it look like we have rotated 90 degrees but the other direction from the first example? Yes, it does. Now this next one, I have a little bit of typo that we need to fix. We're not going to do that right here. This is actually supposed to say 180 degrees around the origin. And ladies and gentlemen, 180 degrees versus a negative 180 degrees are actually the same thing, because a full rotation would be 360 degrees. So whether I go clockwise or I go counterclockwise, it's a half rotation either way. So if we imagine going halfway around, this time it's going to be the third quadrant that becomes my pretend new first quadrant. So I'm going to rotate that around so that that third quadrant becomes my pretend first quadrant. And now I'm going to graph my new 1, 2, my new 3, 1, and my new 1, 1. Connect the dots. And then if I unspin it, then obviously my right angle is my L prime, that real sharp angle is my K prime, and odd man out again is my J prime. So does that look like we've gone halfway around? Yes, it does. This last one is a 90-degree rotation, so we are going to go counterclockwise, but this time instead of around the origin, we're going around the point L. So just like with a reflection, if you touch the line of reflection, you reflect onto yourself. Well, if you touch the center of rotation, you rotate onto yourself. So L is going to be L prime. So I don't really need to worry about that guy. He's nice and simple. The other two, though, before we rotate, it can be helpful to think about where are they compared to that center of rotation. So if we think about J, where is J compared to L? So if this is L, J is one up from L. Now K is to right from L. So if we think about going 90 degrees clockwise, that means I'm going to rotate it so that way it kind of looks like that second quadrant becomes the first quadrant. Now I don't care about that this time, because this time I'm just going to go based on these comparisons. So from my L or my L prime, I'm going to go from this new position 1 up, and that right there is my new J prime, right there. 2 to the right is going to be my K. So from here to the right, 1, 2, that's going to be my K prime. So if I unrotate it, connect the dots, we said that this is my K prime, this is my J prime. And so that's what it'll look like if we do it from some other point than the origin. All right, ladies and gentlemen, this brings us to our last transformation. However, remember I said that there are only 3 isometries. And we've already done our 3 isometries, so this last one is not an isometry. It is still a transformation, but not an isometry. And we could commonly call it a stretch, but its actual technical name is a dilation. So for a dilation, we're going to have what's called a scale factor. A dilation is going to stretch our figure so it becomes a certain number of times bigger than it used to be, or potentially it could even become smaller if we have a scale factor that's less than 1. It could actually condense it instead of stretch it. So we're saying that we want to have a scale factor of 3 from the origin. So to figure this out, what we're going to do is we're going to start with M, and we're going to think, how would I get, if I were to follow all the grid lines, how would I get from the origin, my center of dilation, up to M? Well, I would go 1 to the right and 3 up. So a scale factor of 3 is going to tell me to multiply both of those by 3, or to do this 3 times. Either way you want to look at it. So if I think about doing it 3 times, I've already gone 1 right and 3 up right there. So do it a second time, 1 right and 3 up. That would connect up to here. And then if I do it one more time, 1 right and 3 up. So that would be my M prime. Or again, you can think of it like multiplication. So instead of 1 right and 3 up, times those both by 3. So 1 times 3 would be 3, so 3 to the right, and then 3 times 3 is 9, 9 up. So just to put some notes on that, so if M is 1 right and 3 up, and m prime is 3 right and 9 up. Scale factor of 3, it's going to be 3 times what it used to be. So now if I go to n, n is 1 to the right and 1 up. So n is 1 right and 1 up. So then n prime is going to be 3 times that. So 3 times 1 is 3. And 1 times 3 is 3. So 1, 2, 3 to the right, 1, 2, 3 up, boom, 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 boom. Or you can think about doing this 3 times. 1 right, 1 up, 1 right, 1 up, 1 right, 1 up. So however you think about it, that, we're going to connect these in a second, so I want to move that over, is my n prime. So there's my first side of this triangle. And then finally O. O is just 2 to the right. So 3 times that, O prime, is going to be 6 to the right. So 1, 2, 1, 2, 1, 2 again, 1, 2 a third time. There's my O prime. And I'm going to try to be careful to do this right here. And so in a dilation, what we should end up with here, since the scale factor is 3, is we should look and see a triangle that looks like it's 3 times bigger than our original triangle. Another thing you should notice, especially with the red lines, is that if you were to draw a line from your center of dilation to each of your prime points, it'll go through the original points of the figure. So down here, this time we don't have a coordinate plane, we just have a grid. So I've got my center of rotation, or center of dilation will be the dot, and I want a scale factor of 2. So for this guy, if we imagine going to this point, we have to go 1 right and 1 up. So we want to do that twice. So 1 right, 1 up, 1 right, 1 up. Boom, 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 boom. There's that guy's new point. Down here, this is 1 right, 1 down. So I want to do it twice. So this is once, and then right 1, down 1. That's twice. Or again, you could look at it 1 right, up, 1 right, 1 up, and then double it. So 2 right, 2 up. Whatever works best for your thinking. This guy way out here, though, I have to go 1, 2, 3, 4 to the right and 1 up. So if we double that, we do it again. 1, 2, 3, 4, and 1 up. Should fall on the same line. And the last one is 1, 2, 3, 4 to the right, but 1 down. So 1, 2, 3, 4 to the right, but 1 down. Connect my dots. And my new rectangle should be twice as big as my previous rectangle. And that, ladies and gentlemen, is the end of our lesson.